In this playlist, we're going to cover real solution behavior. This is Catalyst University. I'm Kevin Tokoph. Make sure to like this video and subscribe to the channel. So real solution behavior is one of those topics that I think, when I had it at least, I thought it was very confusing. A lot of the confusion I feel has to do with the nomenclature of certain parameters, certain variables. If you do a quick Google search, you'll find there's actually a lot of different ways to denote one variable. I like it better when things are labeled very appropriately, so that's what I'm going to hopefully do here and make this topic as digestible as possible. All right, let's define four terms. Let's define Henry's law, Raoult's law, ideal solutions, and ideal-dilute solutions. All right, so let's consider a situation. Let's consider a situation where I have a mixture of two liquids. A lot of this playlist is going to have to do with alcohol. We're gonna have a mixture of ethanol and water. Okay, ethanol and water. We're going to define ethanol as being species A. Okay, ethanol is species A, regardless of whether it's the solute or the solvent. Okay, so we've got ethanol mixed with water in some ratio. All right. Henry's law. What does Henry's law say? Henry's law says that the partial pressure of a gas in the vapor phase. Now, what does that mean? This P sub A in the context of Henry's law, this means that the vapor pressure exerted by some component of the solution. So if we've got our mixture of ethanol and water, let's suppose, we're defining A as being ethanol. Let's suppose we have a situation where there's 5% ethanol and 95% water. Well, clearly in that case, ethanol is our solute. It has some mole fraction. And remember that any component of that solution exerts a vapor pressure. So that 5% mole fraction ethanol exerts some vapor pressure. That's this. That vapor pressure due to the solute ethanol, A, is equal to a Henry's law constant times the mole fraction of A, which in this case is our ethanol. Okay? Now, why did I specify that we want it to be our solute? Well, Henry's law is appropriate, or at least most applicable, when your mole fraction of whatever species you're talking about is very low, close to 0. Recall that mole fractions range between 0 and 1. So when our mole fraction is very low, in other words, when we have a very dilute ethanol relative to the water solvent, that's when Henry's law tends to be appropriate. If you look at this chart right here, and I kind of don't like this, let's just call this X sub A. Okay, A is our ethanol, okay? Forget all the B's, okay? Forget all of those. All right, so you see on this curve, and by the way, the solid line is real solution behavior. That's what we see in reality. The dotted lines are where you plot these equations. So this dotted line is the Henry's law. This one is the Raoult's law, which we'll talk about in a minute. In other words, Henry's law is only applicable at very low mole fractions of whatever solute you're talking about. Whatever species is your defining species, our A, ethanol. Only at low ethanol mole fractions is it appropriate. You see that it actually deviates from ideality very quickly, okay? So keep in mind, Henry's law is only applicable at very small mole fractions of whatever species you're talking about with respect to. In this case, it's ethanol. So if we had a mole fraction of like 0.05, okay, we might have Henry's law appropriate. If we start getting way above that, we can't use Henry's law, okay? Now, Raoult's law. This is one we didn't cover in general chemistry as far as I remember. We did cover Henry's law. But Raoult's law basically says that now we're not dealing with a solute. We can deal with the same species, but now we're assuming that species is now the solvent. So in Henry's law, I said we maybe have 5% ethanol, 95% water. Let's flip it. Let's now use 95% ethanol and 5% water. So we're talking about the same species, but now it's the solvent. So the vapor pressure of that solvent, so ethanol, A is ethanol, the vapor pressure of that solvent is equal to the mole fraction of that solvent, which is ethanol, times the vapor pressure of the pure solvent, or the vapor pressure of pure ethanol. This star that you'll see on some of the vapor pressures designates it's of the pure solvent. So if you had 100% ethanol, what would its vapor pressure be? Okay? And this value right here you can typically find tabulated in some table or something like that. Okay, usually you would have to be calculating this vapor pressure, which is the vapor pressure of ethanol. Okay, you'd have to be calculating this in your particular solution. And you can see here, Raoult's law is appropriate when the mole fraction of your ethanol is very high. So over here on this cadet blue region or gray region of the curve, you can see that here they've plotted in the dotted line Raoult's law. You can see that in the green region it deviates from that, but from a mole fraction of about 0.67 up to 1, at least on this curve, Raoult's law is appropriate. So keep in mind, Henry's law is appropriate at low mole fractions of A. Raoult's law is appropriate at high mole fractions of A. Another way of saying that is whatever species A is, when A is the solute, Henry's law is most appropriate. When A is the solvent, Raoult's law is most appropriate. Okay? So hopefully that makes a little bit of sense. Now, what is an ideal solution? Well, these are not very common, but an ideal solution is one where all the solutes and all the solvents in your solution, they all obey Raoult's law at any mole fraction. So, if you picked a species, let's pick the ethanol in that situation, it would literally have to follow Raoult's law, this dotted line, and if you extended it down to the origin, it would have to follow that exactly for all mole fractions. It would just be a straight line if you plotted it. Same thing with the water component. The water would also have to follow Raoult's law. Now, in this figure, the solid line is a real solution, and you can see that in this case, it clearly is not ideal. In fact, I presume that the number of ideal solutions you'd actually run across are fairly low. Most things are real behavior. So we have what's called ideal-dilute solutions. This is sort of a confusing term because it has the term ideal in it. This is a real solution type of behavior, okay? It's not necessarily ideal, it's more of a real behavior. So what is an ideal dilute solution? Pick your species that you're talking about. Let's say it's ethanol in our situation. When ethanol is the solvent, so when it's at a high mole fraction, it must obey Raoult's law, okay? Same species, ethanol. Now assume it's the solute, a low mole fraction. At a low mole fraction, that ethanol would have to obey Henry's law. So what the ideal dilute solution basically says is that under different conditions, it has to obey certain laws. When ethanol in our situation is at a low mole fraction, it must obey Henry's law. When it's at a high mole fraction, it must obey Raoult's law. It doesn't really matter in the middle as long as we satisfy those two conditions on either end of the spectrum. Okay? And if those two conditions are satisfied, we can use the formulas and everything for ideal dilute solutions. Okay? So hopefully that makes sense. Let's go on to a little bit more detail. Okay? So again, let's define Henry's law. It is the partial pressure of the gas in the vapor phase, or it's the vapor pressure of the solute. The vapor pressure of the solute is equal to the Henry's law constant for that solute times the mole fraction of that solute. Okay, and it says that this partial pressure of this partial vapor pressure of that solute is proportional to its mole fraction, and the proportionality constant is the Henry's law constant. Okay. Also, Raoult's law's definition. So we're going to imagine the solution is composed of A, which is the solvent. Then the observed vapor pressure of the solution is proportional by the mole fraction of the A solvent to the vapor pressure of the pure solvent, assuming it was all ethanol. So if we have our situation from the previous slide, the vapor pressure of ethanol, assuming it was the solvent, is equal to its mole fraction times the vapor pressure of pure ethanol, which again, this last one, something you can look up in a table. Now, in honor of physical chemistry basically turning people into alcoholics because of its stress, I've decided to do an alcohol-based example here. So I've got a table here, and for each of these fluids, these solutions I should say, I've tabulated the approximate percent water and percent ethanol, okay? Ultimately, these are not the mole fractions technically, but they will serve the same purpose here. Let's consider water. Water is obviously 100% water, and it's no ethanol in it, okay? So this would have a mole fraction. Let's just assume these percents are like mole fractions. They're not the same, but we're just going to assume that for the sake of argument. So this would have a mole fraction of 0. This would have a mole fraction of 1, at least the water would. This is pure water, Okay, but now let's increase the amount of ethanol a little bit. So now this is really good, by the way, Not Your Father's Mountain Ale. It's like an alcoholic Mountain Dew beer. 5% ethanol, 95% water. Okay, let me ask you a question. If we consider the species A as being, so A or whatever it is, if we consider A to be the ethanol, do you think that this would be under Henry's law's control or Raoult's law? Well, if we're considering that our solute or our A species is ethanol, then this would probably be under the control of Henry's law because the solute, meaning our species A, has a very low mole fraction relative to the solvent water. Okay? So we're probably over here somewhere on this curve. We're in this light blue region, so we're probably under Henry's law's control. Okay? So this would probably at least satisfy the Henry's law component of the ideal dilute solution definition. Okay? Now let's increase the ethanol percentage quite a bit. We're going to go up to Jim Beam vanilla whiskey, 35% ethanol, 65% water. Now we're somewhere over here on the curve. We're somewhere in the middle. We're increasing the amount of ethanol. Now we're deviating from ideal behavior because we're no longer following Henry's law. We're now in this region. We're now definitely in real solution behavior. Okay? Let's increase the alcohol percentage even more. We've got Bacardi 151, 151 proof, so 75.5% ethanol, 24.5% water. Now we're probably over here. Probably over here on the curve in this cadet blue region. So this would actually be following Raoult's law, plausibly, because the mole fraction of our A is now within this region. If we consider A to be our ethanol, okay, now we're under the region that's satisfied with Raoult's law, okay? And now we have to look at this equation. Our vapor pressure due to ethanol would be equal to the mole fraction of ethanol. Again, 75.5% is not the mole fraction, but it would be about the same. The mole fraction of ethanol times the vapor pressure of pure ethanol, which you could look up in a table. So we're about right here for that. And then if we go up to this, which is, I would not recommend drinking this. I mean, people have died doing this, but 100% ethanol. Basically 0% water. This would be like the pure ethanol. Whatever the vapor pressure of this guy is, that would be this number right here, the vapor pressure, assuming it was pure ethanol. And so hopefully now you kind of understand what each component on the curve is. Don't worry about the B's and the A's. Just assume it's all for A, and then just look at different solutions with different proportions of A. Here we have no A, here we have a little bit of A, and then here's all A, and then here's just a lot of A, okay? So think of it like that, all right? Now, Henry's law is pretty straightforward in this form. We have the vapor pressure of the solute A, or vapor pressure, is equal to Henry's law constant times the mole fraction of that solute A, okay? Now, for Raoult's law, we already introduced this formula, but we also have another equation that basically illustrates a similar thing. So the one we're used to dealing with now is the vapor pressure of A, assuming it's the solvent. So now we have mostly ethanol. This is like our Bacardi 151, okay? The vapor pressure of that ethanol is equal to the mole fraction of that solvent ethanol times the vapor pressure of pure ethanol. That's what we talked about being Raoult's law, right? Raoult's law has another sort of equation that describes it, and it's this. The chemical potential of ethanol, in other words, our solution, is equal to the chemical potential of pure ethanol plus this RT natural log of the mole fraction of A, okay? So if this equation is also satisfied, which you really don't do calculations with this is sort of a conceptual thing for the most part, but if it's satisfied with this equation, then it's satisfied by Raoult's law also. So now what I'm going to do is I'm going to go to this slide to conclude this video. Now, here I have this equation of Raoult's law in terms of A, and here I have it expressed in terms of I. I just means any species within the solution. But this is Raoult's law, right? Now, ideal solutions do follow Raoult's law for all mole fractions between 0 and 1. We've already established that. That's a definition of an ideal solution. However, when we don't have an ideal solution, when we have maybe an ideal dilute solution, which is what this graph is plotting on the solid line, we can't use Raoult's law to figure out what's happening in this green region, right? We also can't use Henry's law. So what we have to do is we have to introduce a correction factor, all right? And instead of using this mole fraction, we're going to use activity, okay? So now we're going to have the chemical potential of the species is equal to the chemical potential of the pure species plus RT times the natural